So hello everyone. Let's get started. First of all, apologies because this talk was scheduled for yesterday, but we had some logistics problems with plane, and the organization kindly approved to postpone it. So this is happening now. So my name is Luis. I'm an OpenStack operator in the CERN IT department. And today, together with Enrico, one of our storage experts and Ceph operators, will tell you about our journey exploring storage business continuity and disaster recovery strategies with Ceph and OpenStack. But before getting started, a bit of context. So for those of you who don't know what CERN is the largest particle physics laboratory in the world. We have thousands of physicists getting a better understanding of the fundamental laws and particles of the universe. And to do that, we build a series of accelerators, where the biggest one is the Large Hadron Collider. It's a 27-kilometer ring, 100 meters underground, where we accelerate particles to close to the speed of light. And in different points of this ring, we make them collide in these detectors. And they are responsible of measuring the energy of these particles, the trajectory, many other aspects. And this generates a lot of data because there are 40 million per second of these collisions. We filter them out, and then we store the ones that the scientists consider interesting. To process all this data, we have to provide computing power to the scientists to analyze, to reconstruct, to simulate, and also to offer many IT services to all these experiments. That's why since the 70s, the IT department runs its own data center. And a few years back, in order to make a more efficient usage of these resources and also the operations, we built our own cloud infrastructure based on OpenStack and Ceph. And after some prototypes, it was exactly July 10 years ago that we went into production. And this cloud changed dramatically how the department works and how it interacts with the IT resources. And it's thanks to more than 80 people that work in these teams for the last 10 years. Some of the names that you will find familiar in the community. These 10 years have been 10 years of strong collaboration between the two teams to deploy different cloud offerings for storage in OpenStack, from Glance, Cinder, Manila, and then also object storage. And part of this success has been thanks to something that was mentioned in a paper a few years back, that OpenStack model has simplified operations of core IT and LHC services to consumer storage. Ceph is not used to process or store the bulk of all the collisions that happen in the LHC, but it's used virtually in all the IT services across the organization, from code repositories, monitoring, batch, HPC. Also is used as a backend for many of the storage services in the department, NFS filers or AFS, for instance, and also used by the physics community to deploy different frameworks for monitoring, microelectronics, engineering applications, beams. And also, another aspect that we see the success of this combination is the increase on the offering of Ceph clusters in the department. So basically, they have way many clusters more than before, with different configurations with spinning disk, different spinning disk SSDs, different configurations with erasure coding, more specialized setups with hyperconverts for some of these, for some deployments. And these clusters serve different purposes. The main ones are here. So RBD for mainly Cinder, where we have more than 7,000 volumes, around 4 petabytes of storage use, different volume types to match all these combinations of clusters. The next one is CephFS, that this was one of the latest ones to be in production, but it has seen an increase in growth, thanks in particular to our OpenStack offering and also to the Magnum Kubernetes clusters. And in this case, we have more than 5,000 shares and around 2 petabytes of data used. Then there is also Rados Gateway to offer a S3 compatible API through OpenStack, where we have around 1,000 buckets and almost 1 petabyte of data use. And then a couple of more specialized use cases with a cluster in a second location at CERN for backups, and also clusters to support other services like the CERN tape archive project in the IT department. But even if it's been a few years of a successful cloud offering, our job is not done. The IT department has some challenges ahead. Basically, connected to the fact that our accelerators are continuously being upgraded. And we have a major upgrade coming that is called high luminosity LHC that will increase the number of collisions in the accelerator 10 times to what we have now. This implies for us that we have to provide more compute capacity, more storage needs will come from the experiments. Also, all the experiments that are exploring new architectures, new platforms to analyze this data in a more efficient way. And from this side, there is a growing interest in GPUs, ARM, so this means that for us, we will have a more heterogeneous cloud in years to come. If you want to know more about this area, there's a talk that, this was scheduled for yesterday, but this talk is happening right now. So I guess ideally you can see the recording afterwards, given by Ulrich, one of our colleagues in this area. And there is also one of the priorities in the new CERN IT strategy is to strengthen our BCDR strategy. So basically we want to improve all the building blocks that we offer to our users to deploy BCDR scenarios from network, storage, compute. And storage is the topic of today. And to support all these cases, for the last years, the CERN IT department has been building a new data center that this will be finished by the end of this year. Basically, this new data center is organized in 3 floors. There are 2 rooms per floor. It will offer a total of 12 megawatts of capacity that we plan to fill in 3 different phases, basically 1 phase per floor. And each of these floors, they have 1 UPS that serves these 2 rooms. And it covers around 20% of the capacity in this data center that will be used for services, BCDR, while the rest will be used for batch computing. The good thing of building a new data center from scratch is that we don't have many legacy constraints that we have in our main existing data center, where we have to deal with some limitations in terms of how we match availability zones to failure domains and these sort of things. Also, this new data center will run same stack as we have been running now, so basically OpenStack, different services that we run, and Ceph for the storage offering. And the idea is that this new data center will be a different region separated from the existing one, so we want to enforce users to deploy in these different 2 regions their applications and limit or restrict the cross-region deployments. Also, in terms of availability zones, as I said before, there's a UPS per floor. So the idea is that our availability ranges will match each of the floors in, availability zones will match each of the floors in the new data center. And then we will offer different server group policies if then we need to do more fine-grained scheduling. But one of the key points that we want to work on in this new deployment is the storage. And to do that, we have explored different areas around block storage, file system, HA availability, in order to have more information to do appropriate decisions for the designs that we have to make for this new data center. And it's here where Enrico will tell you about.
Yeah, thank you very much, Luis. So just one spoiler alert, all the beautiful pictures are gone. Now it's getting a bit more technical, unfortunately for you. As you may know, Ceph provides 3 different types of storage. You have block, you have file system, and S3. The rest of the talk is mainly focused on block and file system. And then I have a couple of final slides around higher availability across the 2 data centers. So let's start with block storage. Block storage was the first type of Ceph-based storage that we have integrated with OpenStack. This was 10 years ago, as Luis has mentioned. As it typically happens, you start with 1 cluster, and then the cluster grows. It scales horizontally. You cycle it through different hardware generations. It all worked perfectly until the day we hit one severe bug in 2020. And that was the time at which we have realized that a cluster is very reliable, but may be a single point of failure by itself. So since then, we have worked on a plan to spread RBD storage onto multiple different clusters. And over the last 2 years, we have actually moved from 1 cluster hosting all the volumes that we had to 5 different clusters in order to reduce the impact that a cluster being unavailable would have on the work of the organization. As you can see, the number of clusters has increased a lot. The number of volumes hasn't changed too much. We have consolidated the volume types according to the quality of service that they provision. We have standard and IO1 on spinning disks, IO2 and IO3 on full flash, SATA SSDs. We also have some special gold-plated volume types that are hosted on nodes in a special room of the data center, which is backed by diesel generators, so they would survive a long power outage on the site. The QoS aspect is quite relevant for our end users because what we did initially was to basically get a new cluster, create new volume types, and the volume types were encoding both the physical location of the cluster and the QoS. And everyone was extremely confused on what to pick because the differentiation was not that clear. So we have had another thought on this. We decided to consolidate on QoS, and we have introduced what we call storage availability zones. I'm pretty sure you're all extremely familiar with availability zones for compute. We are trying to mimic the same concept for storage. So basically, in OpenStack at CERN today, you can go and ask for a standard volume, and this is actually backed by 3 different clusters, 3 different Ceph clusters, in different rooms, different power feeds, different network branches, different everything. So to reduce the likelihood that an incident in the data center brings down more than one storage cluster at the same time. If the users do not care about where the data goes, they just ask Cinder to create a volume for them, and Cinder has a sort of internal weighting function to pick the best candidate. But if they know what they want to do precisely, they can still explicitly ask to have the volumes hosted on a specific cluster. As you see in the example here, I'm creating a volume which is OpenInfra 23, and it goes to the storage availability zones, which is called Ceph Geneva 3. So having multiple RBD clusters helps in business continuity. I will talk more about business continuity later on, especially for what concerns the cross-data center consistent storage. And now we will actually transition into backups, which are more related to the disaster recovery plans that we have. We have investigated different ways of doing RBD backups. One is a Ceph internal mechanism, which is called RBD mirroring, and it's not covered in this talk. I had another talk at Cephalocon, and tomorrow during the Ceph Day, where I will cover also this aspect. But today we actually focus on the Cinder backup drivers. So Cinder has the ability to do RBD backups in many different ways. You can have backup drivers, different backup drivers accordingly to the storage technology that you want to use to store your backup onto. We focused on 2 of those, which are the S3 driver and the Ceph RBD driver, just because we operate these technologies and we are familiar with those. And we actually started with the S3 because we use X3 already extensively for many other backup purposes. And we benchmarked the driver, which unfortunately it's not very exciting in terms of performance. The plot here, it basically shows the time it takes to back up volumes with different sizes, either 1 or 5 gigs, which can be either empty, half full, or completely full. If you take the blue bar as a reference, this is a 5 gigs full image, and it takes 6 or 7 minutes to back it up. So it's quite a long time. This doesn't really match our expectations. There are some parameters that you can tune because what the driver does behind the scenes is that it reads the source image, it makes chunks, compresses the chunks, and uploads them to S3. But all these parameters are not really a game changer in terms of performance, and there are always trade-offs. If you want to be storage efficient and save space, or if you just want to be fast and have your backups done as quickly as possible. What actually works extremely well out of the box is the backup driver to write Ceph RBDs onto another Ceph cluster that does Ceph RBDs. The main reasons for this is due to the fact that the driver uses low-level Ceph features and capabilities and libraries. Also, it basically relies fully on librd. The performance are very good out of the box. You can write backups at 140, 150 megabytes a second. As you can see, the time is proportional to the size of the image here from 1 gig to 1 terabyte. What is also very important for us is that this scales well with the number of concurrent backups that you're doing at the same time. So basically, the network becomes your problem, and you're no longer CPU bound or memory bound. Incrementals are also super good. Again, we are using low-level Ceph features, which are very effective in making the work more efficient. This is a plot that shows the time taking to do an incremental backup when you're changing a given amount of bytes in the source image. And this given amount of bytes, we have tested it in different contexts. It goes from 1% to 32%. The resulting time does not precisely match the time, the amount of bytes that we change in the source image, but there is a sort of a trend, and this is very consistent, and so we're pretty happy with the result. One thing that we're trying to provide, which is not fully implemented yet, but we're working on it, is to do backups cross sites. This basically means that whenever we have a source image in data center 1, for instance, we want its backup to be stored in the second data center, just to leverage the geographic distance between the two. As Luis was mentioning, we are trying to cut as much as possible the crosstalk between the two data centers. So what we plan to have is actually to run 2 Cinder controllers, which are fully decoupled one from the other. And in principle, they do not even know that another Cinder controller exists. Which makes things a bit more complicated, because if you want to restore a backup in the second data center, this guy here, the Cinder controller in the second data center, is not aware of the fact that the backup is available. You can work around this. Cinder provides a way to export the metadata backup. You get a blob, and then you re-import the blob into the second Cinder controller. And this would basically make the second Cinder aware of the fact that there is a backup in the Ceph cluster co-located in the very same data center, which then can be used to restore from in case the first data center goes completely unavailable. So in this scenario, the Ceph cluster and the Cinder controller in the surviving data center would be fully autonomous in doing a restore. I was saying this is not fully implemented yet because this mechanism to do export and import of metadata is a sort of an asynchronous process, which we would need to implement. It's not actually related to the process of backing up the volume itself. But there is a blueprint out that describes the multi-backend support in Cinder, which would definitely help us in taking care of this issue, at least partially. So we're definitely looking forward into the evolution of this proposal and in testing the multi-backend support in Cinder. So this closes the part about block storage, RBD, and Cinder. We go to file systems and Manila shares. So in CERN OpenStack, the Manila shares are actually backed up by CephFS. CephFS has a capability to do snapshots of file systems by itself. This is precisely what you think it does. A snapshot, it's a point-in-time consistent view of a file system which you cannot change. Operating CephFS snapshots is very easy from the user perspective in the sense that you just enable this feature cluster-wide, and then the owners of the snapshots the owner of the shares can go and create subdirectories into a special directory, which is .snap, and basically whenever they create a directory there, a snapshot is taken, and the same is for deletion. This is a very valuable feature. It would unlock many, many options. For instance, the snapshots are immediately readable by the very same clients, so users could recover previous versions of files or deleted files. We could use the snapshots to do the backups, either by using external tools or by using Ceph itself with another mirroring feature, which is similar to the one implemented for RBD. Basically, Ceph would make a copy of the file system from one source target to another, from one source cluster to a target cluster, according to some snapshotting mechanism that it implements. But the main problem that we're facing is that snapshots do have a price, and you basically pay a performance price. So these are two cumulative distribution functions of the time it takes to untar the traditional Linux kernel archive, which we always use to do tests, and then to remove all the files that were unpacked from the compressed archive. As we have repeated the test, I think 100 times or maybe 200 times, either with snapshots not enabled, which is the green line, or with snapshots enabled, which is the red line. And basically, the mismatch between the two lines, it tells you the performance impact, the performance price that you're going to pay if you're using snapshots on CephFS. I just want to make clear that this is something that you see only when you have very intensive metadata workload, and when you're doing this at scale, we have petabytes of CephFS at CERN. If you're running a very small cluster or with very few users doing intensive I/O operations, maybe this is completely, it goes below the radar for you. It would not be a problem. We are actually looking into ways to work these around. The problem seems confined into the metadata server. So one could, for instance, run 2 MDSs at the same time and pin all the shares that need snapshots onto one, which will be slower than expected, and instead pin all the remaining CephFS shares that do not need snapshots on the other MDS, which has more CPU cycles available. This is something we are experimenting. We're not very confident at the moment to enable snapshots in the wild. So we're looking actually into other solutions to do CephFS backups. We have one tool internally at CERN, which is called CBAC. This was built on top of restic, with the difference that we have implemented stateless agents. So you can have basically as many backup or restore or prune agents as you want, and the state of the backup is actually kept in a central MySQL DB. So whenever there is a backup to be executed or to be restored, the agents go to the DB, they get a lock, and they do the work. We use this to back up some of the CephFS that we have, and another service which is called CERNbox. It's our sync and share platform. And currently on a daily basis, we do 40,000 backups, and we have a total of almost 6 petabytes of data backed up to S3 with this machinery. Machinery which we are trying to improve. We would like to add support for writing backups to tape. We have a huge tape pool at CERN, which is mainly used for the physics data. We would like to use it more for IT-related backups and needs. We would like to support multiple S3 endpoints. This was actually implemented so that the end users can decide whether they want to use our S3 endpoints or an external S3 provider. And last but definitely not least, we're working on implementing a client that we would distribute to the users so that they are fully autonomous in looking into the backups that they have and restoring. How does this relate to Manila? So as far as I know, as of today, there is not a backup driver in Manila which is similar to the one that was implemented for RBD. There is another machinery which is called share replication, which is mostly meant for high availability. It can be stretched to some extent for supporting backups, but it's not necessarily the best thing to do or the thing you want to do. So again, reading mailing lists, there are discussions on how to do backups for Manila. We are pretty much interested into this. We would like to understand if there is an interest in supporting CephFS snapshots and mirroring natively in Manila, or if we can somehow integrate it with CBAC. CBAC, for instance, provide an API, so Manila could simply query CBAC to understand what's the backup state and configure new backups. A couple of very last slides for what concerns cross-data center highly available storage. So you may have heard about Ceph stretch mode. This is a mode of operation of a Ceph cluster where you have data in 2 data centers plus an additional monitor in a 3rd data center, which can be the cloud or it can be whatever you want, which is just meant to identify net splits or other glitches going on and basically decide whether one of the 2 data centers is actually gone. We have tested this out. It works very nicely. It comes with a slightly higher price tag because you go from traditional replica 3 to replica 4. Erasure coding is not supported at the moment. The good thing is that you would have consistent storage across the 2 data centers, and actually the operations are synchronous. If you write something on one side, this gets immediately mirrored on the other side with no delay. The problem that we're facing is how to integrate this with Cinder and Manila, because as we were saying from the very beginning, the deployments are expected to be completely decoupled one from the other. So Ceph would provide the storage, but OpenStack would not be able to use it, or at least immediately. There are ways to work around this. We could have a global region that basically embraces the two data centers and takes advantage of this distributed storage. We could also foresee a sort of a manual emergency operation. If one data center goes down, we spawn an emergency Cinder and Manila on the surviving data center with the backed up information from the controller, which is now unavailable. So it's something that we are testing. It's a bit unclear at the moment where is the sweet spot between complexity and functionality that we want to offer. Similarly for S3, we use S3 a lot. It was not covered too much in this talk. Ceph also provides S3 Rados Gateway multi-site. It's pretty similar to Stretch Cluster, though it's not fully identical. Writes are not synchronous in this case. There is a replication delay between the two sites, but it's definitely valuable. And in this case, the integration with OpenStack, it's pretty much easy because the only thing we query OpenStack for is to track the quota and to track the credentials, which are things which clients would know anyway. So OpenStack is absolutely not in the line of fire when the client has to reach out to the Rados gateways and do IOs on the storage. Okay, conclusions. We do not have our conclusions on this talk. It's a very exploratory work. And we are at the Open Infra Summit. We are very happy to talk to every one of you if you're facing these issues or similar issues and understand how you're tackling these problems. So indeed, it's an ongoing work. There are many, many decisions to be considered and to be taken. So we are looking forward to talk to you. And if you have questions, we are happy to take them now and also start some discussions offline. Thanks a lot. Questions? No question. Oh, there is a question.
Does Ceph's stretch mode impact latency?
So the question is, does stretch mode impact latency? From what we have measured, no. It is also true that the latency between our two data centers, it's very low. So if you have two data centers which are 100 milliseconds apart, I would guess this becomes visible. Because the way this operates is that you acknowledge a write to a client only when the write went through to the other data center as well. The client always talks to one OSD on either side, and then this gets replicated internally. So there is some latency component. But for the nature of our deployment, we are unable to see this. Yeah. Question.
Yeah, for the RBD availability zones, are you just relying on the users to make smart decisions on storing your data
So,
in different locations, or is there something that's
someone knows. Someone doesn't necessarily know how to make best use of the storage. The problem is that we also do not know. And these things are typically growing over time, and it's pretty hard to, let's say, counterbalance the expectations that they have with the technical solution that we are implementing. Maybe because they started to do something and they are not aware of the fact that we provide some other features, or yeah, there are many, many cases. We have some cases which we know precisely, and then we encourage the owner of those cases to use storage in a given way. We have like a top tier, super critical services, and we constantly talk to the people running these services to make sure that everything is as clean as possible. The other case in which we guide the users is for the critical power use case. So for instance, we have some hypervisors under diesel power, and if we see that they have quota or they ask for quota in storage, which is not under critical power or vice versa, we go and we tell them and we make them aware of the fact that if, for instance, we have a prolonged power cut, the storage will be down. And we actually suggest them to use storage which is in the critical power zone.
This case is why we went for, or we are planning to go for this schema of having the new data centers at different regions. This implies a lot of constraints for the users, but we minimize the funny scenarios where people are deploying here, mounting data from the other side in the wrong way. So we try to minimize that case and just make people run on one or the other region and then have the availability zones, but yeah, to minimize this case that they have to do super smart decisions because we have our user base is quite mixed.
Any other question? I think I actually forgot the outro slide. You can come and visit us, and there is a Ceph Day tomorrow co-located with Open Infra if you're more interested into storage things. Thanks again.